Hello there, and welcome. Tonight, we'll drift back before time, before stars, before even the concept of before existed. We're going in search of something nearly impossible, how everything came from nothing. Not just the Big Bang, but the mystery that surrounds it. What was there before time? How did energy, matter, and even space itself unfold from a single point, or maybe from no point at all? We'll explore the strange clues hidden in quantum fields, in ancient radiation, and in the math of the universe itself. Some say there was a vacuum, others a multiverse, and some believe nothing might not be so empty after all. It's a story with no clear beginning, but endless possibilities. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Nothing is a strange word. It sounds simple, like an empty bowl, a cleared page, a breath held too long. But when we look closer scientifically, philosophically, even emotionally, it becomes slippery. We use it often in everyday life. There's nothing in the fridge. I feel like nothing matters. There's nothing left to say. But even in these moments, we're rarely talking about true emptiness. We're describing absence, a missing something, which means that nothing only makes sense because we know what something is. But what if we try to go further? What if we ask, what existed before the universe, before time, before matter, before space? Was there truly nothing? To understand how everything began, we must first understand what nothing isn't. For centuries, philosophers debated whether true nothingness could exist at all. Aristotle rejected the idea entirely. He believed nature abhorred a vacuum, that there could never be a place with no substance, no form, no potential. In ancient Greece, nothingness wasn't simply a lack. It was impossible by definition. Meanwhile, across the world, in early Taoist and Hindu texts, nothingness was treated not as void, but as a kind of fullness, an origin space, infinite and pregnant with potential. The Tao Te Ching begins by saying, "The Tao that can be named is not the eternal Tao," hinting that the moment we try to label the beginning, we've already misunderstood it. Nothingness, here, is sacred, not a whole, but a silence that births sound. But when science began measuring the universe, it found something stranger still. Even when you remove everything, particles, light, heat, something remains. In the quantum world, a perfect vacuum isn't perfectly empty. Space itself, stripped of matter and cooled to absolute zero, still crackles with activity. Tiny particles blink into existence, then vanish. Energy flickers briefly, then disappears. It's called quantum fluctuation, and it suggests that what we call nothing might actually be a storm beneath stillness. This isn't hypothetical. In 1948, an experiment by Dutch physicist Hendrik Casimir revealed that two metal plates, placed very close together in a vacuum, would slowly attract each other. Not because of any charge, not because of heat, but because the quantum vacuum between them wasn't truly empty. It had pressure. The nothing pushed. And this is where our definition begins to bend. Because if a vacuum still has properties, if it has energy, if particles can pop in and out, then what exactly is it missing? Some scientists now believe that the universe may have emerged from this kind of quantum nothing, that space itself is not passive, but a field, humming with potential. That if you wait long enough, in the right conditions, entire universes can form the way bubbles rise in boiling water, sudden, spontaneous, and inevitable. If that's true, then maybe we've been thinking about nothing all wrong. Maybe it's not a black void, but a seeding ground, not a pause, but a low whisper beneath the song. Because this kind of nothing isn't nothing. It's full of invisible potential, like the still air before a thunderstorm, waiting for a single shift. But the questions don't end there, because even if our universe emerged from a quantum vacuum, where did that come from? What gave rise to space, to fields, to the laws that govern them? Why does something exist at all, rather than pure non-being? This is where science begins to tremble at the edges of its own language. Physics can explain what happens once time begins, but not why time exists. Mathematics can describe how particles behave, but not where the rules come from. It's like standing inside a library that built itself, reading books no one wrote, printed on paper that wasn't made. Some physicists have tried to solve this by proposing that the universe is a zero-sum system, that the positive energy of matter is exactly balanced by the negative energy of gravity, that when you add it all up, the total energy of the universe is zero. And if that's the case, then creating the universe costs nothing. In fact, it might be the most natural thing for nothing to do. But again, this is not the kind of nothing we think of when we stare into darkness. It's an elegant balance, a perfect equation, a kind of cosmic accounting, and still, we're left with the unease, a silence that feels deeper than physics can explain, because we can trace the moments after the Big Bang measure, them, even. We can describe the inflationary burst, the cooling plasma, the formation of atoms and galaxies and stars. But the trigger, the ignition point, remains hidden. Was there a cause? Was it random? Was there even a before? At this edge, physics begins to sound like poetry. Some propose that our universe is one of many, that in a vast multiverse, bubbles of space-time form endlessly, each with different rules, different constants. In that view, our cosmos isn't unique. It's just one expression of a deeper, timeless structure that births universes the way trees drop seeds. And in that deeper space, maybe nothing has no meaning at all. Others say the question itself is flawed, that asking what came before time is like asking what's north of the North Pole. Time is part of the structure, not something that existed before it. If so, then nothingness isn't a place or a state. It's a boundary, a limit to the questions we can ask. But there's something haunting about the idea that nothing might not exist at all, that there is no true emptiness, no clean slate, that even the most silent void may still be whispering, still fluctuating, still dreaming of light. And maybe that's the strangest part of all, because here you are, lying still in your bed, in the quiet of night, listening to a voice about how nothing became everything. You're made of atoms, carbon, calcium, iron that once burned in stars. But those atoms themselves emerged from a chain of causes that stretches back to a time with no space, no direction, no distance. You are evidence that nothing may not be empty, that silence gives rise to sound, that even in the deepest vacuum, something stirs. You are a ripple in what was once thought to be still, a thought in the mind of nothing. And maybe that's where everything begins. Imagine a room with nothing in it, no light, no air, no walls, no atoms drifting lazily in the background, a space cleared of everything absolute, untouched, and perfectly still. We like to think that this is what empty means, but in physics, the closer we try to approach nothingness, the more it slips through our fingers. Even when we strip away all visible matter, all radiation, all known forms of energy, something invisible remains. Because space, even the quietest, darkest space, is not empty at all. It is ruled by hidden laws, filled with unseen tension, and alive with fields that ripple beneath the surface. At the heart of this lies quantum field theory. It tells us that every particle we know, electrons, quarks, photons, is not a separate entity, but an excitation in an underlying field. These fields stretch across the universe like invisible fabrics draped over space-time. Wherever you are, no matter how far you travel, you are immersed in them. There is an electron field, a photon field, a gluon field. They are always present, even in the darkest reaches of the void. And even when there are no particles around, the fields are never perfectly flat. This is the strange truth of the quantum world. The lowest energy state, the vacuum, is not silent. It quivers, it stirs. Quantum uncertainty forbids stillness. Instead, the fields jitter with spontaneous fluctuations, like a sea that never fully calms. These ripples create pairs of particles and antiparticles born from nothing, flickering into existence and then annihilating each other before they can be seen. They are called virtual particles, and they are everywhere. You cannot bottle them, you cannot point to them, but they change how things behave. These momentary ghosts affect how light bends around charged particles. They shift the orbits of electrons. They even alter the force between metal plates in a vacuum, a phenomenon known as the Casimir effect, an actual, measurable force pulled from what we once thought was empty space. That small tug between plates is not caused by air, pressure, or magnetism. It's caused by the fact that in the quantum vacuum, there's always something dancing, just beyond the edge of observation. Even the vacuum has energy. It is not a placeholder for nothingness, but a dynamic, physical entity with weight, consequence, and rules. This vacuum energy is not theoretical. It shows up in equations. It may even be responsible for the expansion of the universe itself. Some scientists believe it's tied to dark energy, the mysterious force that is driving galaxies apart, faster and faster, as though space were stretching itself from within. It's difficult to overstate how revolutionary this is. When Einstein proposed the fabric of space-time, he imagined it as smooth and continuous, a flexible sheet that could be curved by mass, but otherwise uniform. Quantum theory shattered that simplicity. It showed that, beneath the calm, space is filled with layers, patterns, probabilities. Nothing is truly nothing. Beneath zero, there is still movement. Beneath silence, there is still sound we cannot hear. What makes this even stranger is that these fields, with all their complexity, still obey rules. They follow symmetries and equations that govern their behavior across all of space and time. It's not chaos, but a kind of hidden choreography. When a particle appears, it does so according to strict principles. Conservation of energy, conservation of momentum, laws that still hold, even when there's no observer, no experiment, no laboratory. Even in the blankest parts of space, the universe is not lawless. This is one of the great mysteries of physics. Why are there rules at all? Why does a photon always behave the same way, whether it travels through a lab in Switzerland or across a void a billion light-years wide? Why does the speed of light have a universal limit? Why do particles obey statistics, obey charge, obey spin, even when they rise from quantum foam? Some physicists argue that these rules are baked into the fabric of reality, that they are not laws imposed upon the universe, but expressions of its most fundamental nature. Symmetry, in particular, seems to lie at the root of everything. Certain symmetries in physics, when preserved, give rise to conservation laws. Others, when broken, allow for particles to gain mass, for forces to differentiate. It's through symmetry and its breaking that complexity arises from simplicity, order from the restless void. There's something haunting about this, that even in emptiness, structure exists. That space is not just a backdrop, but a participant. In the coldest, darkest corners of the cosmos, where no star shines and no atom spins, the fields still hum. They remember the rules. They obey patterns older than time. They continue their quiet dance, indifferent to whether anyone is watching. In 2012, the discovery of the Higgs boson, a particle associated with the Higgs field, confirmed something long suspected. that even the property of mass, something so fundamental to our sense of matter, emerges from a field that fills all of space. The Higgs field is not turned on or off. It's always there. You are moving through it now. Every second of your life, you are brushing against a universal presence that gives particles their weight. You don't feel it, but your very existence depends on it. It's hard not to be awed by that. The sense that space is not passive, but alive. That emptiness is not empty, but woven with tension and structure. That the rules of physics are not just convenient tools we've written down in textbooks, but the quiet laws whispered into the bones of the universe. And so, we're left with a paradox. The more we study nothing, the more we find. Not absence, but presence. Not silence, but potential. The vacuum of space may seem empty to the eye, but to the laws of quantum mechanics, it is teeming with fluctuation, energy, and possibility. And maybe, in the beginning, that's all it took. A fluctuation, a ripple, a shift in a field that could not stay still. And from that light, matter, stars, everything, far beneath everything you see, beneath atoms, beneath particles, beneath the smooth curve of space and time, there is something wild, a place so small and strange that our rules begin to break down. Zoom in far enough, and space stops being still. It writhes, it folds, it changes shape in a frenzy of unpredictable motion. It bubbles like boiling water, not with heat, but with potential. This is the realm of quantum foam, and it may be the closest we've come to understanding the true foundation of reality. The term was coined by physicist John Wheeler in the mid-20th century. He imagined that at unimaginably small scales, distances close to the Planck length, about 100 million trillion times smaller than a proton spacetime itself, begins to act more like a liquid than a solid. Not a calm liquid, but one constantly stirred by quantum fluctuations. In this chaotic zone, particles pop in and out of existence. Space curves, twists, and reconnects. Time itself may lose its meaning. Imagine the smooth surface of a pond. From above, it looks still and glassy, but drop down to the level of individual droplets, and you'll see a storm, a mess of eddies, swirls, ripples, and collisions. The surface isn't flat at all. It's alive with motion. This is what physicists believe may be happening at the very base of everything. What appears to be solid, predictable space is, at the smallest scale, a churning sea of possibilities. It's not just particles that are temporary here. Even geometry becomes uncertain. The distance between 2 points may fluctuate. The concept of location becomes fuzzy. At this level, nothing stays where it is for long. There may be no such thing as continuity, only sudden shifts from one configuration to another. In quantum foam, space-time is not the stage on which events unfold. It is one of the actors, constantly improvising its lines. The weirdness of this realm comes from quantum mechanics itself. At small scales, uncertainty reigns. You can't know both the position and momentum of a particle exactly. Energy levels fluctuate. Particles exist in superposition states that are neither one thing nor another. In the foam, these effects aren't rare exceptions. They are the rule. And this chaos isn't limited to particles. It applies to the very fabric of space-time. The smooth grid imagined by Einstein buckles here. General relativity, which describes the curvature of space-time, meets quantum theory, which describes uncertainty and fuzziness. But when you try to combine them at this scale, the math breaks. Equations spin off toward infinity, gravity, and quantum mechanics clash. We do not yet have a complete theory of quantum gravity, but whatever form it takes, it will have to make sense of this boiling mess. Some scientists believe that in this foam, microscopic black holes could form and evaporate in a flash. Others think wormholes, tiny tunnels connecting distant regions of space, may blink in and out of existence. Not stable ones you could travel through, but ghostly shortcuts that flicker for less than a heartbeat. The entire geometry of the universe, at this scale, could be filled with holes, tears, and loops too small to see. What's even more unsettling is that this restless, bubbling foam may be the origin of everything we know. According to some theories, the universe itself could have emerged from a fluctuation in this field of chaos, a tiny ripple that grew, expanded, and unfolded into the vast cosmos we see today. Not from a place, but from instability itself, from a moment when the foam surged just enough to become something larger, and that surge wasn't guided, it wasn't planned. It may not have had a cause in the traditional sense, it could have just happened, because in quantum mechanics, fluctuations happen all the time. The question is whether they fade or take root, whether they disappear or become a universe. We don't have microscopes that can peer directly into the foam. It's too small, too fleeting, but its effects echo upward. Virtual particles affect real processes. Vacuum fluctuations shape cosmic inflation, and the structure of the universe, the stars, the galaxies, even the shape of the cosmic microwave background may carry the fingerprints of those earliest quantum jitters. It's humbling to think that the solid world around us, mountains, oceans, skin, and breath, rests on a storm, that every moment of stillness floats atop a sea that never sleeps, that beneath the lines of reality, something is always shifting. This is not a void, but a forge, not emptiness, but raw invention. And if we could stand at that scale, if we could feel the foam rise and fall beneath our feet, we might hear the first murmur of the cosmos, the quiet, restless sound of something trying to become. In the quietest places we can imagine, silence isn't what it seems. An empty vacuum, a region stripped of every atom, every photon, every trace of heat, should feel like nothing, a blank canvas. But the universe refuses to be still, even in the dark. At the smallest scales, that vacuum isn't empty at all. It seethes with invisible energy. Flickers of existence spark and vanish in intervals too brief to measure. These are virtual particles, ghosts of matter that ripple through space without ever fully becoming. They're not like the particles we know. They don't linger, don't travel, don't leave trails we can follow. They exist for just long enough to bend the rules of physics, then dissolve. And yet their presence is felt, their influence is real. In this hidden layer of reality, even nothing has structure. It hums with possibility. The reason comes down to quantum uncertainty, the same principle that says we can never know both the position and momentum of a particle with perfect precision. Applied to energy and time, this uncertainty allows for brief moments where conservation of energy can be bent, as long as it's paid back quickly. In those fleeting instants, particles can emerge from the vacuum. A pair, one matter, one antimatter, flickers into being, borrows energy from the vacuum itself, and then annihilates, leaving no trace behind. To us, it seems like a trick, a violation, but in the quantum world, it's allowed. These particles may not be directly observable, but they have weight in the equations. They influence the behavior of real particles, change the way forces operate, and alter the fabric of space itself. They're woven into the math of the universe, as unavoidable as gravity or light. In fact, their fingerprints are everywhere. The most famous example comes from the Casimir effect, a strange attraction between two metal plates placed very close together in a vacuum. There are no atoms between them, no visible force pulling them, and yet they drift together, gently but measurably. The reason lies in virtual particles. Outside the plates, the vacuum is teeming with activity fluctuations and ripples from all directions. But between the plates, the space is so narrow that many wavelengths of virtual particles are excluded. Fewer fluctuations happen in the gap than around it. This imbalance in pressure creates a push, not from something but from the subtle difference in the energy of nothing. It's a quiet force born from the invisible restlessness of empty space. The energy tied to these fluctuations is called vacuum energy. And though we can't see it directly, we're starting to understand just how profound its effects may be. In cosmology, vacuum energy is a major candidate for the mysterious force known as dark energy, the driver behind the accelerating expansion of the universe. Galaxies are drifting apart, not just from momentum, but as if space itself is stretching, carried outward by some hidden energy embedded in its own nature. That energy might not be an afterthought. It might be fundamental. Some theories suggest that the vacuum energy of space, the constant thrum of virtual particles and quantum fields, isn't just a background feature. It may be the reason the universe exists at all. Think of it like a field filled with hills and valleys. The vacuum isn't flat, it has shape. And depending on where you are in that landscape, how much energy the vacuum has, it can tip the balance toward creation. If a small patch of space enters a higher energy state, it can destabilize. And in that destabilization, a bubble can form. A bubble of new space, a new universe. This is one of the leading ideas behind cosmic inflation. That, in the earliest moment of time, a small region of quantum vacuum entered a state of high energy, then expanded rapidly, stretching faster than the speed of light. It inflated like a balloon, smoothing out irregularities and flattening the geometry of space. When that inflation ended, the energy was released, converted into heat, light, and matter. The Big Bang wasn't an explosion from a point, but a phase transition, a shift in the vacuum state, from something unstable to something stable, from seething potential to the physical cosmos. All of this, from virtual particles that don't last, from energy we can't touch, from a vacuum that isn't empty. It's a difficult idea to hold on to, that everything we see, galaxies, planets, breath, skin, fire, could have emerged not from a singular object, but from the latent properties of space itself, from the way nothing never truly sits still, from fluctuations so brief they defy our clocks. But in a quantum universe, time and space are not static backgrounds. They are part of the play. They shift, bend, and react to the energy within them. And the vacuum is never quiet. Even now, in the spaces between atoms in your body, in the silent distances between stars, virtual particles flicker and fade, countless times every second. The vacuum boils beneath your feet, beneath your breath. It is not absence, it is a wellspring. Perhaps the most poetic truth in all of physics is this, that what we call nothing, what we once believed to be void, emptiness, non-existence, is, at its heart, the birthplace of everything. A blank page that cannot help but write itself. And somewhere, buried in that whisper of potential, the first note of our universe began. In the vast stillness of deep time, the Big Bang sits like a heartbeat, sudden, foundational, and endlessly echoed. It wasn't an explosion in space, the way fire leaps from fuel or stars tear themselves apart. It was the birth of space itself. Time, distance, matter, energy, everything we know emerged not from a place, but from a moment. A change so complete it didn't leave a before, only an after. What we know begins at roughly 13.8 billion years ago, not with fire, but with expansion. The entire universe compressed into a state so dense, so hot, that the very laws of physics were warped into forms we barely recognize. It's called a singularity, but that name is more placeholder than explanation. A mathematical whisper that at this scale, our current models fail. Still, from this searing origin, the cosmos began to grow, not outward, like an object tossed into the air, but everywhere, all at once. Space itself stretched, carrying matter with it. Every inch of emptiness expanding, every point rushing away from every other. Within the first trillionth of a second, the universe changed dramatically. It inflated, faster than the speed of light, smoothing out wrinkles and scattering irregularities. This brief exponential burst was not the Big Bang itself, but what followed, what we call the hot Big Bang, set the stage for everything. Quarks and gluons, the building blocks of protons and neutrons, danced in a high-energy soup. Light could not travel freely. The universe was opaque, dense, and turbulent, a storm of particles in chaotic conversation. We can't see this early moment directly. There are no photos of the beginning, no snapshots from the birth. But like detectives at the edge of a crater, we've learned to read the patterns left behind. One of the most powerful clues is the cosmic microwave background faint radiation that bathes the universe, coming from every direction. It's not light from stars or galaxies, but from a time before either existed. A relic from when the universe was just 380,000 years old and finally cool enough for atoms to form. For the first time, photons, light particles, could travel freely, escaping the fog of charged particles. That light is still with us. We catch it with satellites and radio telescopes, like listening to an ancient voice whispering through static. And what it tells us is remarkable. The cosmic microwave background is almost perfectly uniform, with only the slightest ripples, tiny variations in temperature and density, seeded by quantum fluctuations from the very beginning. These ripples became the scaffolding for all structure in the universe. Galaxies, stars, clusters, all the great formations we see trace their origins back to these faint whispers in the background, imperfections that gravity would later pull into shape. We also know the universe is still expanding. When we look at distant galaxies, we see them receding from us, not because we are at the center, but because space itself continues to stretch. The further a galaxy is, the faster it appears to be moving away. This discovery, first made in the 1920 seconds by Edwin Hubble, confirmed that the universe has a history. It had a younger version of itself, a smaller, hotter, denser past. And if we rewind the clock far enough, all paths converge on a single origin point. But for all that we know, the Big Bang holds its silences. We don't know what triggered it. We can model the expansion, the formation of particles, the birth of atoms, and light, but we don't know what set it in motion. Was it a quantum fluctuation, a phase change in some deeper field? Was it the rebound of a previous universe collapsing inward, a cosmic breath out after a breath in? Or was it the beginning of time itself, with no before to speak of? And what of the singularity? The idea that the universe began from a point of infinite density and temperature remains a puzzle. Our equations suggest it, but infinities in physics are usually signs that something deeper is missing. We don't yet have a quantum theory of gravity, a framework that unites Einstein's smooth spacetime with the jittery probabilities of the quantum world. Without it, the first moment remains hidden behind a veil we cannot yet lift. There are also hints that the universe may be part of something larger. Multiverse theories suggest our cosmos could be one of many, born from a larger landscape of possibilities. In that view, the Big Bang wasn't unique, but one bubble among countless others, each expanding into their own separate space. Some may have different laws of physics, different constants, different fates. We can't observe them directly, but mathematically, they remain on the table. And then there's dark energy, the strange force accelerating the universe's expansion. We don't know what it is or why it behaves the way it does, but it may hold clues about the vacuum, about energy embedded in space, and about how the universe might end or begin again. Even time is a question. Did it begin with the Big Bang? Or is time an emergent property, a result of entropy and change, not something that existed in the pure state of the beginning? If so, then the universe wasn't born into time. Time was born inside the universe. Still, what we can say with confidence is that we are children of that first flash. Every atom in your body was forged from the aftermath. Hydrogen from the Big Bang's cooling fire. Carbon, oxygen, and iron from stars that came later, kindled by the gravity that those early ripples made possible. The glow of that beginning still surrounds us, silent and ancient, encoded into the sky. The Big Bang is not just a theory of origin. It's a bridge between what we know and what we don't, between the visible and the invisible, between the fire of beginning and the long, slow unfolding of everything that followed. And when we look out into the night, we're not just seeing stars, we're seeing time stretched thin. We're seeing history lit by light that took billions of years to reach us. A reminder that the beginning is never truly gone. It's still unfolding, still expanding, still with us now. Long after the fires of the Big Bang faded, after the first atoms formed and the early chaos cooled into silence, something remained. A faint echo stretched thin across the sky, not in light we can see, but in microwaves, long, low-frequency ripples that fill the universe like a quiet breath still lingering from its first exhale. This whisper, the cosmic microwave background, is the oldest light we can observe. Not light from stars or galaxies, but from a time before either existed. A snapshot of the cosmos when it was still young, still settling, still deciding what it would become. This light has been traveling for more than 13 billion years. It began its journey when the universe was just a newborn, around 380,000 years old. A blink, really, on cosmic timescales. Before that moment, space was too hot, too dense, too wild for light to move freely. Photons were constantly bouncing off charged particles, scattered like marbles in a storm. The universe was opaque, like a glowing fog. But then, as expansion stretched the cosmos and temperatures dropped, something changed. Protons and electrons finally cooled enough to combine into hydrogen atoms. With fewer charged particles to interfere, light broke free, and in that moment, the universe became transparent. That released light is still here, still moving outward, still wrapping around us in every direction. We call it the cosmic microwave background, or CMB. And though it is unimaginably old and dim, it carries secrets etched into its delicate ripples, secrets about the birth of everything. The discovery of the CMB was almost accidental. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working on a sensitive antenna in New Jersey. They kept detecting a persistent background noise, steady, isotropic, and impossible to filter out. At first, they suspected pigeons nesting in the equipment, but even after removing them, the signal remained. Unbeknownst to them, theorists had already predicted this afterglow years earlier as a consequence of the Big Bang. The match was perfect. What Penzias and Wilson had stumbled upon was the oldest light in the universe. It changed everything. Suddenly, the Big Bang theory wasn't just plausible. It was written across the sky. When we observe the CMB with precision instruments, like those aboard the Planck satellite or the earlier COBE and WMAP missions, what we see is more than just a glow. It's a map, a record of minute temperature differences, just millionths of a degree from point to point. These tiny fluctuations represent density differences in the early universe, areas where matter was ever so slightly more or less concentrated. And from those differences, all future structure emerged. Gravity pulled on the denser regions, drawing in more matter, snowballing into stars, galaxies, and the web of clusters we see today. In a way, the CMB is the universe's baby photo. But it's more than just an image. It's a key. The pattern of ripples tells us about the shape of the universe, the amount of dark matter and dark energy, the rate of expansion, and the age of everything. It shows that space is remarkably flat, meaning parallel. Lines would stay parallel forever, and that the ingredients of the universe are not just visible matter, but mostly invisible forces. It's hard to believe that such vast truths are locked inside a field of radiation barely 3 degrees above absolute zero. The CMB is now just 2.725 Kelvin, a chill so deep that it would freeze hydrogen solid. But it wasn't always so cold. Back when it was released, the universe was 1,000 times hotter. As space expanded, the wavelength of the light stretched too, cooling along with it. What began as a brilliant orange-white glow is now a faint microwave hum. Still, even in its dimness, it speaks. It speaks of symmetry and its breaking, of inflation and quantum fluctuations, of a time when space and energy danced more freely, when the rules we know today were just beginning to emerge. But it also leaves us with questions. Why is the CMB so smooth when the universe had so little time to even out its differences? Why do certain regions show slight anomalies, subtle cold spots, or asymmetries that theory struggles to explain? Are these just statistical quirks, or signs of something deeper, perhaps a hint of another universe brushing against our own? There are theories that the CMB holds imprints from the multiverse, a gentle bruise from a neighboring cosmos. Others suggest that features in the CMB could reveal the shape of the universe itself, not just in space, but in the flow of time. If time loops, or if the cosmos is shaped like a higher dimensional surface folded back on itself, the background radiation might carry those fingerprints. And yet, for all its mysteries, there is something soothing about the constancy of the CMB. No matter where we look in the sky, we find it, uniform, persistent, patient. It reminds us that the universe has a memory, that long after the brightest explosions fade and the last stars dim, the glow of origin remains. You can't hear it with your ears, but if you had an old analog TV and tuned it to a channel with no broadcast signal, a small fraction of that static on the screen, just a whisper, is the CMB, still arriving. A fragment of ancient light passing through your living room. To gaze into the CMB is to look not just backward in time, but inward, toward the seed of all things. Every galaxy, every atom, every idea you've ever had, all of it came after that moment. And though it grows fainter with each passing eon, it still holds the shape of what we are. A silent hymn that never stopped singing, a whisper that carries the weight of the beginning. Time begins to blur when we drift too close to the origin. The further back we trace the history of the universe, the hotter, denser, and more chaotic everything becomes. Equations tighten, temperatures soar, and eventually we arrive at a kind of wall, the Big Bang. It's not just a point in time, but a boundary in understanding, a place where our models of physics shudder and collapse under infinities. For decades it was treated as the beginning of everything, the start of time, space, motion, meaning. But what if it wasn't? What if that flash was not the first moment, but only the latest? In recent years, physicists and cosmologists have begun to peel back the curtain on that threshold, using new tools of mathematics, new interpretations of quantum mechanics, and daring speculation to imagine what if anything came before. Not because they are dissatisfied with the Big Bang, but because the equations suggest there might be more. Because silence is often where the deepest stories hide. One idea begins with a bounce. Rather than the universe beginning from nothing, some theories propose it is the result of a collapse. A previous universe, vast and ancient, may have grown cold and empty, then reversed, shrinking inward until it reached an impossibly dense state. Then, with a kind of gravitational recoil, it rebounded our Big Bang, not a beginning, but a rebirth. This is the essence of a cyclical or bouncing cosmology, a rhythm of creation and destruction, expansion and collapse, pulsing across time like a breath that never ends. This view suggests the universe might be eternal, not in a static sense, but in a rolling wave of epochs. Each cycle erases the scars of the last, smoothing space and resetting entropy. We would live not in the first cosmos, but in one of many, separated by fire and silence. Another perspective draws from quantum gravity, our attempts to unify the smooth space-time of general relativity with the unpredictable flickers of the quantum world. In these models, time itself may not be fundamental. It could be emergent, a byproduct of relationships between particles, not a fabric of its own. If time is not basic, then before the Big Bang may not even be a meaningful question. There may be no before, not because nothing existed, but because the notion of before breaks down at that scale. In loop quantum cosmology, space is not continuous, but made of tiny loops woven together like threads in a fabric. At extreme densities, these loops push back against gravity, preventing a singularity from forming. Instead of reaching infinite density, the universe rebounds, skipping over the classical singularity entirely. The bounce becomes part of the natural evolution, and the Big Bang is no longer a sharp beginning but a transition point, an inflection in an eternal arc. Then there are theories inspired by string theory and higher dimensions. In these models, what we perceive as our universe is a three-dimensional membrane called a brain floating in a higher dimensional space. Other brains may exist parallel to ours, and the Big Bang could be the result of a collision between two of them. The crash would inject immense energy into our brain, igniting a universe. In this scenario, what we see as a beginning is just a bruise from a larger, multidimensional event. Perhaps most haunting of all is the possibility that the universe emerged from a quantum vacuum, a roiling sea of probabilities, where fluctuations can briefly form something from nothing. Given enough time, even the smallest possibility becomes inevitable. A closed bubble of space-time could spontaneously appear, inflating into a full universe. In this view, the cosmos is not birthed from something else, but from the inherent instability of nothing itself. The vacuum is never truly empty. It is restless, and from its ripples, a universe can bloom. But even these bold ideas carry shadows. They trade one mystery for another. If our universe came from a previous one, where did that first universe come from? If time is emergent, what governs its emergence? If the vacuum can birth reality, what defines the vacuum? At each step, the ground recedes. And yet, perhaps that's the point. Our search for what came before the Big Bang is not just about physics. It is a mirror for our longing to find continuity, to trace the thread backward, to believe that something always was, that the world we know rests not on an accident, but on a deeper, more ancient rhythm. Still, the universe may not owe us answers. It may only offer hints, gravitational waves that tremble through space-time, tiny imprints in the cosmic microwave background, equations that balance only if something larger lies behind the veil. We follow these signs, knowing they may never lead to certainty, but also knowing that even uncertainty is a kind of understanding. To ask what came before the Big Bang is to confront the limits of knowledge itself. It is to stand at the edge of what can be known and listen carefully for what echoes from the dark. Maybe we will one day build instruments capable of glimpsing into that past. Maybe we'll find signatures of a bounce, or of other brains, or of cycles stretching back through uncountable eons. Or maybe we won't. Maybe the beginning will always be a kind of horizon, not a wall, but a place where vision fades, where our maps end, and wonder begins. And in that silence, before the first light bloomed, before space had shape or time had meaning, perhaps there was not nothing, nor something, but the quiet inevitability that one day there would be. Imagine standing at the edge of everything, watching the horizon of our known universe curve away into silence. The stars thin, the galaxies fade, and beyond them stretches an ocean we cannot cross, not because we lack the tools, but because what lies past that boundary may not belong to our universe at all. For all our awe at the scale of the cosmos, what if this entire reality, the space between atoms, the galaxies spinning in darkness, the light from the first fire is only a small bubble in a vast unseen sea? The idea sounds like science fiction, but it grows not from imagination, but from mathematics, from the logic of inflation and the strange consequences of quantum uncertainty. At the end of the Big Bang's explosive beginning, Our universe went through a phase of rapid expansion. In the blink of an eye, space stretched faster than light, smoothing itself out and scattering quantum ripples that would later become stars and galaxies. But in the equations that describe this inflation, there's no reason it had to stop everywhere at once. In fact, it's more likely that it didn't. Instead, in some regions, inflation ends and a universe like ours condenses from the cooled energy. But elsewhere, inflation continues. And from that eternal inflation, new bubbles form, new pockets of space where inflation stops and a new universe begins. Each bubble, a cosmos unto itself, each with its own laws, its own constants, perhaps even its own version of physics. This is the multiverse, not a poetic metaphor, but a real possibility arising from our best understanding of how space, energy, and probability interact. In this view, our universe is not the whole story. It's one page in a cosmic novel with infinite volumes. Some pages might look similar universes with stars and gravity and particles like ours. Others might be utterly alien, ruled by forces we can't imagine, or by nothing at all. The concept feels overwhelming. We're used to thinking of everything as a final word, a closed container. But in the multiverse, everything becomes local. Your everything is not the everything. It's just what inflation happened to leave behind in this bubble, this chapter. And there are versions of the multiverse that don't even need eternal inflation to work. In the many worlds interpretation of quantum mechanics, every possible outcome of every event actually happens but in a separate, branching universe. When you flip a coin, in one world it lands heads, in another, tails. When you choose one path, another version of you takes the other. These branches split constantly, endlessly, creating an infinite forest of realities, each with its own thread of history. There are other models still. Some suggest the multiverse exists in higher dimensions, with brains floating in a wider dimensional space. Others arise from string theory, where the number of ways to compactify extra dimensions results in a landscape of possible universes, each one shaped by different configurations of strings and fields. If this seems speculative, it's because it is. We can't yet test these ideas directly. Other universes would, by definition, be beyond our observable horizon. The light from them could never reach us, and their physics might be incompatible with ours. But they are not unscientific. They arise as consequences, not assumptions, of theories already supported by data. Still, there's a quieter question nestled inside all this cosmic branching. Why is our universe the way it is? Why does it have just the right balance of forces and constants to allow for stars to form, for chemistry to happen, for life to emerge? It's called the fine-tuning problem. If the strength of gravity were slightly stronger or weaker, if the charge of the electron were different by even a fraction, atoms might never hold together, stars might never ignite. Time might unravel before anything could unfold. In a single universe model, this feels uncanny, arbitrary, lucky. But in a multiverse, it becomes less strange. If there are countless universes, each with different parameters, then some will inevitably have the right conditions for complexity to arise. We find ourselves in such a universe not because it's special, but because only universes like this can contain observers asking the question. It's not design, it's selection. Still, the idea of a multiverse can feel unsatisfying, even lonely. If other universes exist, but we can never reach them, never touch them, are they real in any meaningful way? Are we forever trapped in our bubble, surrounded by infinite possibility we can never confirm? And yet, even in its solitude, the thought expands us. It stretches the boundaries of humility. It reminds us that our view of reality is shaped by the limits of perception, that the silence between galaxies may not be the end of the road, but the edge of our candlelight. There may be scars in our sky, cold spots, patterns, or anisotropies that hint at collisions between our universe and others, long ago, before the cosmic microwave background cooled. There may be indirect effects, subtle deviations in the values of constants that one day lead us to evidence, or perhaps we'll never know for sure, and the multiverse will remain one of those profound ideas that cannot be proved or disproved, only contemplated. Either way, it asks us to consider that reality is more generous than we imagined, that creation may not have happened once, but endlessly, that we are part of a grander pattern, one we cannot fully see, but that surrounds us like the soft echo of a distant song. Maybe we are not alone, not even in being alone. Maybe existence itself is an infinite unfolding, and our universe, with all its beauty and strangeness, is simply the verse we happen to sing. Close your eyes and imagine the absence of everything. Not a dark room, not empty space, not a silent forest at night, but the true, total absence of anything at all. No shape, no time, no thought, no distance. Just a stillness so complete it doesn't even know it's still. Can such a thing be imagined? Can it be known? Or is nothing only a shadow cast by something, a concept that depends on contrast to exist? Long before science built its instruments and theories, before particles and quantum fields and cosmological constants, human beings asked these questions in the language they had: words, stories, paradoxes. Philosophy, after all, was our first attempt to make sense of the universe. And in its earliest forms, it turned often toward nothingness, not as a vacuum to be feared, but as a mystery to be met. In ancient Greece, the philosopher Parmenides stood at the threshold of reason and refused to cross. Around the 5th century BCE, he argued that nothing could not exist because to think of nothing was, paradoxically, to make it into something. If you can speak of it, if you can name it or conceive of it, it must in some way be. And therefore, in the purest logic, only being exists. Change, movement, even time, all illusions. For Parmenides, reality was singular, unchanging, and eternal. There could be no creation ex nihilo, no emergence from a void, because the void itself was impossible. His argument was radical and unsettling, and it clashed with everything experience seemed to show. Yet it formed a wedge in the history of thought, one that philosophers have been wrestling with ever since. His student Zeno, famously, took this logic and twisted it into paradoxes: the arrow that never reaches its target, the tortoise who always stays ahead, each a challenge to the very idea of motion and division, all rooted in the strange implications of what it means for something or nothing to be. But across the world, in the valleys and mountains of ancient China, a different kind of nothingness was being shaped, less rigid, more poetic. In the 6th century BCE, Lao Tzu composed the Tao Te Ching, a collection of verses that explored the Tao, the way, the source, the path that underlies all things. The Tao was not a god or a force in the Western sense, but something deeper and more subtle, a flow, an origin that gives rise to form without itself having form. Lao Tzu wrote, "We shape clay into a pot, but it is the emptiness inside that holds whatever we want." And 30 spokes share the wheel's hub. It is the center whole that makes it useful. In these lines, absence is not a failure of presence, but its enabler. The void is not terrifying, it is fertile. What is not there gives meaning to what is. Here, nothingness becomes a kind of presence, a necessary complement. In Taoist thought, non-being is not the enemy of being, but its partner. The two exist in balance, in rhythm. One gives birth to the other, endlessly. Just as silence shapes music, just as space shapes form, so too does the void shape existence. These ideas echoed in Buddhism, particularly in the concept of shunyata, or emptiness. Not mere blankness, but the insight that all things are empty of fixed, independent identity, that everything is interdependent, arising in relation, impermanent, ever-changing. Emptiness is not nihilism, it is liberation from illusion. In the Heart Sutra, a foundational Buddhist text, it is written, Form is emptiness. Emptiness is form. The two are not opposites. They are the same. In India, meanwhile, other philosophers were struggling with similar questions. The Samkhya school proposed a dual reality, Purusha, the eternal witness, and Prakriti, the ever-changing material world. In this view, the self exists beyond the realm of things, untouched by form or time. The material world is full of motion and complexity, but the true self rests in stillness, beyond description. Later, Advaita Vedanta would take this further, claiming that all of reality is one Brahman, infinite and without division. The individual self, or Atman, is not separate from the universe but identical to it. Separation is illusion, and if all is one, then the apparent dance of creation from nothing is a trick of the mind. There was never a beginning. There was never a void. There is only this, eternal and indivisible. In the West, centuries later, Christian theology would wrestle with creation ex nihilo, the idea that God created the world out of nothing, not shaped it from chaos or molded it from existing matter, but called it into being by sheer will. It was a different kind of nothingness, an emptiness that lay before time itself, punctured by divine command. But even this raised difficult questions. Can we speak of before time? Can a void contain the potential for action? And in more recent centuries, philosophers like Heidegger and Sartre would return to the question of nothingness, not in the cosmic sense, but in the personal. What does it mean to be? What is it like to confront the void, not out there, but within? For existentialists, nothingness was a confrontation, a tension. We define ourselves in its shadow. It is the silence that allows us to choose. Across cultures and centuries, the thread remains. Nothingness, far from being a simple idea, is one of the most slippery and profound concepts we have ever tried to grasp. It is not merely the absence of matter or the end of thought. It is a mirror, held up to our need for explanation, our hunger for origin, our fear of emptiness, and perhaps our love of mystery. For in the end, to ponder nothing is also to reach for everything, and to imagine the void is, always, to fill it. Long before telescopes scanned the sky or particle accelerators, shattered atoms, humans looked into the dark and asked how it all began, not with equations, but with stories, woven into language and memory, passed from breath to breath across generations. These myths of origin were our first attempts to explain the unimaginable. They weren't simply tales told for comfort, they were frameworks of meaning, maps drawn in metaphor to describe what lay beyond understanding. And as strange as it may seem, buried within some of these ancient narratives are echoes, faint, resonant chords that now hum through the language of science. In Hindu cosmology, creation begins not with a bang, but a breath. The Rig Veda speaks of a time before time, when there was neither existence nor non-existence. No sky, no earth, no air, no light. Only the great cosmic waters, silent and still. And within that stillness, a single impulse stirred desire. From this seed, the universe unfolded, not all at once, but rhythmically, as part of an endless cycle. In Hindu thought, the universe is not created once and for all, but expands and contracts in great waves. Brahma's day and night, billions of years long, each cosmos born, sustained and dissolved in turn. This idea of cycles, of expansion and collapse, bears a curious resemblance to certain modern models of cosmology. The concept of a big bounce, where our universe is one phase in a repeating loop of contractions and rebirths, finds a distant kinship in these ancient verses. Even the language of emergence from stillness feels oddly familiar, as if the vacuum fluctuations that seeded matter were being described through poetry rather than physics. In the book of Genesis, creation unfolds through speech. "Let there be light," says the voice, and there is light. Order follows chaos, separation of sky and sea, land and air, life from dust. In 6 days, the world is shaped not from nothing, strictly speaking, but from formlessness, a void over which spirit hovers. It is a story of division, of boundaries, of naming things into existence. And while it speaks in days, not epochs, its cadence has a structural logic that mirrors the layering of physical processes, the cooling, the clustering, the emergence of complexity from a single initiating command. Even the opening phrase, "in the beginning," echoes the modern notion of a singular start point, a first moment from which time and space unfurled. And while science does not speak in the language of divine intention, it does agree that everything we now observe, every star, every cell, every thought emerged from an origin so compact and strange, it defies simple description. In the cosmologies of the Maori, creation begins in darkness. In Te Kore, the great nothingness, from this void comes Te Po, the long night. And only after enduring many nights does light break forth, and the gods Ranginui and Papatuanuku, sky and earth, emerge. But they are locked in embrace, their children trapped between them. It is only when the children force them apart that space is made, and the world begins. A tale of separation and emergence, of pressure and release, a myth of tension, a primordial confinement followed by expansion. There's an uncanny echo here in the inflationary epic of our universe, when space itself expanded faster than light, a sudden pushing apart that allowed matter and structure to take form. Though one speaks of gods and the other of fields and metrics, both describe creation not as spontaneous appearance, but as a transformation, a breaking open of what once was sealed. The Yoruba of West Africa tell of a time when the world was only sky and water. The god Olodumare sends the deity Obatala to create land. Armed with a snail shell filled with sand, a chicken to scatter it, and a palm nut to plant life, Obatala descends and fashions the earth. Here, creation is not a single explosion, but an act of deliberate unfolding, piece by piece, from above to below. There's a slowness to it, a sense of guided evolution, and perhaps it's this same unfolding we now try to model with simulations and telescopes, tracing how hydrogen clouds collapse into stars, how dust becomes planets, how conditions slowly ripen toward life. In Norse mythology, the universe begins in a yawning gap, Ginnunga Gap. To the north lies Niflheim, the realm of ice and mist. To the south, Muspelheim, a land of fire. Where these opposites meet, life begins. From melting ice and rising heat, the first being, Ymir, emerges. The cosmos is born not from a void, but from a collision of extremes. And again, we hear the whisper of thermodynamics, the interplay of energy and entropy, of heat and order. In this myth, matter arises from tension, from contrast, from the friction of opposites. So many myths begin not with substance, but with void, with darkness, water, silence, or gap. They recognize, in their own way, that nothingness must come first not as an end, but as a kind of preparation, a stage waiting to be set. And though they differ in symbols and tone, a pattern emerges, a formless state, a stirring, a transformation, a cosmos born not randomly, but with rhythm. Modern cosmology now speaks in numbers, radiation maps, and statistical variance, but at its core, it still seeks what the myths sought, the beginning, the place where questions outnumber answers, where time itself may not yet tick. It peels back the sky, layer by layer, looking for the moment when the lights first flickered on, and it often finds, in its cold precision, something strangely poetic. Perhaps it's because both science and myth are human acts. They use different tools, but they rise from the same longing to know where we came from, to name the beginning, to understand how something, this breath, this thought, this galaxy could ever arise at all. And in that shared pursuit, the distance between the mythic and the scientific narrows, because even now, in our age of instruments and data, we are still telling stories in the dark. Time is so familiar that we rarely notice its strangeness. We feel it in the way shadows lengthen, in the way skin wrinkles, in the stillness that follows a heartbeat. It's the current we drift along, always from one moment to the next, never backward. We remember yesterday, but not tomorrow. We grow older, never younger. Ice melts, but it does not spontaneously refreeze. A cup shatters on the floor, but never reassembles itself. This direction, this flow, is what physicists call the arrow of time. But why should time have a direction at all? And was it always pointing the way it is now? In the equations that describe the universe, Newton's mechanics, Einstein's relativity, Schrödinger's wave functions, there is no preferred direction. The math works just as well forwards as backwards. A bouncing ball can be played in reverse, and the laws will still hold. The universe, according to its raw code, doesn't seem to care which way time moves. And yet, the world we experience cares very much. This tension between time-symmetric laws and our time-asymmetric lives is one of the great puzzles of modern physics. The most widely accepted explanation comes from the realm of thermodynamics, the study of heat, energy, and disorder. Specifically, the second law, which states that entropy, the measure of disorder in a system, always increases over time. In other words, things tend toward messiness. Ice melts, smoke disperses, order gives way to chaos. This law introduces an arrow, not because of the laws themselves, but because of probability. There are simply far more ways for things to be disordered than ordered. Given enough time, systems evolve from unlikely configurations to more likely ones. The direction of increasing entropy is the direction we call forward. So perhaps time's arrow is not a fundamental law, but a statistical tendency, a kind of cosmic bias. But this explanation brings its own mystery. If entropy always increases, then the universe must have begun in a state of incredibly low entropy, a state of remarkable order. Why? At the very birth of everything, the Big Bang, the universe was dense and hot, but smooth. No black holes, no galaxies, just a near uniform soup of particles. For such a crowded, energetic place, the entropy was oddly low. That pristine beginning, balanced on the edge of simplicity, is what allows time to move the way it does now. If the universe had begun in a state of high entropy, time might look very different, or perhaps wouldn't exist as we know it at all. Some physicists suspect that the conditions of the early universe were not random, that some deeper principle selected for low entropy. Others wonder whether this low entropy state is merely a fluke, a rare statistical anomaly that we just happen to inhabit. Still others suggest that what we think of as the beginning may not be the beginning at all, that time might extend in both directions, with entropy increasing on either side of a central point. In this model, the Big Bang is not the start of time, but the middle. There's a haunting elegance to that idea. Imagine two universes, back to back, each with time flowing away from the shared moment of origin. To observers in either universe, time feels forward, entropy increases, memories accumulate. But from a wider perspective, if such a thing exists, there is symmetry, no preferred direction, only the illusion of forward motion on either side of the divide. Other perspectives look even deeper. Some theories of quantum gravity suggest that time may not be fundamental at all, that it emerges from more basic relationships like temperature or pressure. In these models, the universe is not a movie playing out frame by frame, but a vast tapestry in which time is a kind of illusion, an emergent property of entangled systems, like the redness of a rose or the warmth of a fire. In quantum mechanics, the arrow of time becomes even murkier. The equations work forwards and backwards. Particles do strange, seemingly timeless things existing in multiple states, jumping between possibilities. It's only when we observe them collapse the wave function that time seems to reassert itself, pinning potential into presence, maybe even creating memory from uncertainty. And then there's the mind. Our perception of time's passage is intimately tied to memory. We remember the past, but not the future. Our brains are wired to encode experience in one direction. This creates a psychological arrow of time, separate from physics, but deeply influential. If we somehow remembered the future and forgot the past, would time feel reversed, or would it feel exactly the same, just flipped? Time is also bound to causality. We expect causes to precede effects, but in some interpretations of quantum theory, effects can influence causes. Particles can become entangled across time. In rare and controversial experiments, future measurements appear to affect past events, at least statistically. These are not violations of causality in the traditional sense, but they hint at a more flexible structure beneath what we perceive. Time might not be a line, but a web. So where does that leave us? We know that time moves forward because entropy increases, because we age, because the night follows the day, but we don't fully know why. The arrow may be a byproduct of initial conditions, a statistical shadow, or something deeper still. And the question of whether time had a beginning remains tangled in the mystery of the universe itself. If time began with the Big Bang, what was it like in those first moments? Did it start suddenly, like a light flicked on in the dark? Or did it emerge gradually, as order separated from chaos, as space found its shape? Could time begin without space, or space without time? And if time began, will it one day end? These questions remain open. They live in the quiet spaces between what we observe and what we imagine. Time may be an arrow, a circle, a branching tree, or an illusion painted over a deeper truth. Whatever it is, we ride it, moment by moment, memory by memory, always forward, never knowing how long the path is or where it began. And maybe, just maybe, time is not something we move through at all. Maybe it is something that unfolds within us. What does it mean for a law to exist when there is nothing to govern? No space in which to stretch, no particles to push or pull, no time to measure one moment from the next. Can a rule be real if there is no playing field? The natural laws we know, gravity, electromagnetism, thermodynamics, relativity, are etched into the fabric of our universe. But were they always there? Were they waiting in silence, before the first flicker of light, before the birth of a single atom? The very question pulls at the edges of imagination. We are so used to the world behaving predictably that we forget how much those behaviors depend on context. Gravity only acts when there is mass. Time only flows when there is change. Space only stretches when there is something to stretch. But what if, before all of this, there was not just no matter or motion, but no framework at all? No canvas, no coordinates, only a still, unshaped potential. In modern physics, laws are not merely instructions, they are descriptions of how things behave. They emerge from observation, from repeated patterns, from the persistent regularity of nature's rhythms. But this means they depend, in some sense, on the existence of a system to observe, a universe to study. Which raises a delicate point. Are these laws fundamental, existing independently of any universe, or are they emergent, rising into being only as the universe itself takes form? Some physicists and philosophers suggest that laws are platonic, eternal, unchanging truths that exist beyond time and space. In this view, even if the universe had never existed, the law of gravity would still be true. It just wouldn't be expressed. It would be like an unwritten poem or a symphony never performed, real, in principle, but silent. Others argue that laws are more like habits, tendencies that crystallize once the universe has cooled and expanded enough to support regularity. Perhaps in the earliest moments, when time itself was only beginning to tick, these laws were not fixed, but fluid. Perhaps they settled into their familiar forms only after the universe found its shape. This leads to an idea called law selection, where different regions or epochs of the universe may have followed different rules. In string theory, there are countless possible configurations of physical laws in different ways that extra dimensions can curl, different strengths for the fundamental forces. Our universe, then, may be one among many possible realities, each with its own distinct playbook. If this is true, then laws are not pre-existing absolutes, but outcomes like the weather, determined by initial conditions and subtle variations. But if laws emerged with the universe, then what, if anything, determined their emergence? Is there a meta-law, a deeper principle that governs the laws themselves? And if so, does that meta-law exist beyond space and time, or within them? Quantum cosmology offers a strange possibility. In certain models, the universe can arise spontaneously from a quantum vacuum, a state of no classical matter, no definite space or time, but still seething with possibility. Even in this nothing, uncertainty reigns. Fluctuations stir. Tiny bubbles of reality blink in and out of being. In such a picture, the laws of physics might emerge as statistical preferences, with the most stable configurations in a landscape of probabilities, not chosen exactly, but favored. Still, this doesn't quite answer the deeper question. Where do those probabilities come from? What determines what can fluctuate, or what is likely? We circle back to the same paradox. To have a universe, we need laws, but to have laws, we may need a universe. Perhaps the trouble lies in the way we think. We imagine time as linear, cause before effect, laws before events. But in the quantum realm, such neat order can break down. Effects can appear without clear causes. Particles can influence each other across space with no signal between them. Time can seem to reverse or disappear altogether. In this realm, maybe the emergence of laws and the birth of the universe are the same event, not one before the other, but simultaneous, co-arising, like a melody and the instrument that plays it. There is also the mystery of mathematics. Why does the universe follow elegant equations? Why can abstract symbols drawn on paper so often predict the behavior of stars and atoms? Some suggest that mathematics is the true bedrock, that reality conforms to math, not because it must, but because math is the most fundamental language of existence. If this is true, then perhaps laws existed before the universe in the way geometry exists before any particular shape is drawn. They are the grammar of potential, waiting for a story. And yet, maybe there was no before. Time itself began with the universe. Asking what existed before time may be like asking what's north of the North Pole. It's not a flaw in the question, it's a clue that our concepts may not apply. If there was no time, there was no waiting, no unfolding, no moment in which laws could lie dormant. Still, something stirred, something that allowed this universe to be rather than not. Whether that something was a law, a fluctuation, a necessity, or an accident, we do not yet know. But whatever it was, it brought with it the strange gift of order. And from that order came stars and gravity and memory and questions. Imagine, for a moment, that everything you see, every tree, every star, every breath you've ever taken, is not the result of atoms colliding over billions of years, but of something else entirely, something synthetic. That behind the gentle hum of the universe, behind the ticking of time and the vast weave of galaxies, there is no fabric at all, only code, a sequence, a simulation. It sounds like science fiction, the kind of idea whispered in the flicker of a late-night film or scribbled in the margins of a theoretical physics paper. But in recent years, the simulation hypothesis has stepped cautiously into the halls of serious thought. It begins with a simple proposition. If it's possible to simulate a universe down to the level of conscious beings, and if some civilization somewhere, at some point in the long stretch of time, develops that capacity, then the number of simulated realities could vastly outnumber the one that gave rise to them. And if that's true, then it may be statistically more likely that we are inside one of those simulations rather than living in a singular base reality. This line of reasoning doesn't require malicious architects or puppeteering intelligences. It only asks, what is more probable, that we are the first and only reality to exist, or that we are part of a cascade, one digital dream inside a stack of others? The idea stretches back further than it seems. In some ways, Plato's allegory of the cave was an early meditation on perception and illusion, on how we mistake the shadows for the real. And in Eastern philosophies, especially in certain schools of Hinduism and Buddhism, the world is described as Maya, a grand illusion, a play of appearances over deeper truths. What modern thinkers have done is translate these ancient intuitions into the language of information theory and computation. If the universe is a simulation, it must be running on some kind of substrate, something more fundamental than atoms or light. In this view, the true building blocks of existence are bits, ones and zeros. Reality becomes a vast unfolding computation where the laws of physics are the rules of the program, and matter is simply how information manifests. The speed of light? A maximum processing speed. Quantum uncertainty? A kind of rendering shortcut. Space-time itself? A user interface. And then there's the strange behavior of particles when observed. In the famous double-slit experiment, particles seem to act differently when watched, collapsing from a blur of possibilities into a single outcome. This isn't definitive proof of a simulation, but it does raise unsettling parallels. In computer graphics, a system often only renders what the user is actively viewing to save on resources. Could reality be doing something similar? Could the world outside your field of awareness be a kind of latent code, waiting for you to look? Even the pixelation of energy at the quantum scale, the smallest discrete units of space and time, resembles the digital resolution of a simulation. Our universe, it seems, has a lowest level, a quantum grain beyond which nothing gets smoother. Just as a screen, no matter how high definition, eventually reveals its pixels up close, so too does the universe reveal its quantized underpinnings. But if we are in a simulation, the question naturally arises, who or what created it? Some speculate it could be a future version of ourselves, a post-human civilization capable of running ancestral simulations, peering back through the lens of history. Others imagine intelligences vastly different from our own, for whom entire universes are no more effort than a dream. Still others resist the idea altogether, insisting that it cheapens reality, that it shifts mystery into an even more impenetrable domain. And what of meaning? If we are simulated, does it diminish our experiences, our loves, our losses, our quiet, private thoughts? Perhaps not. A dream still feels real to the dreamer. A simulated sunset can still stir something in the heart of a simulated mind. If we are code, then that code is capable of beauty, of memory, of curiosity. That, too, is real enough to matter. Moreover, if the simulation is consistent, if it obeys rules and fosters complexity, then its contents, its stars, its species, its civilizations are no less wondrous for having been conjured by algorithms. It only shifts the location of creation. Instead of arising from a singularity, we emerge from a processor. Instead of evolving on a lonely planet, we evolve in an environment crafted with intention, or perhaps randomly generated, the way a game might be. There are, of course, criticisms. Some argue that the simulation hypothesis is untestable and therefore unscientific. Others point out the staggering computational power required to simulate even a single brain, let alone a universe full of them. But advances in AI and virtual reality continue to blur the line between the real and the rendered. As our own simulations grow in sophistication, we inch closer to the mirror. What we once thought of as uniquely biological emotion, insight, even consciousness now flickers within machines. And here lies the final twist. Even if the simulation hypothesis is wrong, the path it opens is real, because we are already building worlds. Every digital landscape, every AI model, every neural network is a step toward becoming the kind of beings who might one day simulate not just a mind, but a cosmos. If it is possible, then eventually it may happen, and if it happens once, it can happen again. We are not merely asking whether we are inside a simulation, we are learning how to become the simulators. In the end, maybe it doesn't matter whether the universe is real or rendered, whether it sprang from a singularity or from a server. What matters is that we are here, thinking, wondering, creating stories to contain the vast unknown. Whether we are characters in a narrative or authors of our own, we still search for meaning in the code. And in that search, something very human persists. Even in a simulated world, wonder is not an illusion. It is the program still running. Numbers have always felt strangely inevitable. Before we ever wrote them down or used them to count the stars, they seemed to be waiting in the curve of a shell, the rhythm of a heartbeat, the spiral of a galaxy. Mathematics doesn't simply describe the universe, it predicts it. Equations scribbled on chalkboards have foretold particles never before observed, described black holes decades before they were imaged, and traced the invisible scaffolding that holds galaxies in place. But what if math does more than model reality? What if math is reality? This is the central claim of the mathematical universe hypothesis, a bold idea proposed by physicist Max Tegmark. According to this view, the universe doesn't merely behave mathematically, it is mathematics. Every particle, every force, every dimension is not a thing in the traditional sense, but a mathematical structure, a geometry, a pattern, a piece of an eternal formula. It's not the first time such an idea has taken root. Long before quantum fields and dark energy, the philosopher Plato suggested that beyond the world of appearances was a deeper realm, a world of perfect forms. Circles that were truly circular, triangles that never wobbled at the edges, numbers that held no approximation. In our reality, everything is an echo, but in this higher realm, there is purity, unchanging truths. And in a way, math has always been our bridge to that world. While cultures differ, while languages shift, mathematical truths remain. 2 and 2 is always 4. The angles of a triangle always sum to 180 degrees, at least in flat space. But if the universe is made of math, it raises a strange kind of question. Did the math exist before the universe, or did the universe bring math into being? It's tempting to think of numbers as timeless, as existing in a kind of abstract nowhere. After all, the number 7 didn't begin when humans discovered it. It didn't evolve or grow. It simply was. In this sense, mathematics seems independent of us, and perhaps even independent of matter. We don't invent math, we uncover it, like archaeologists brushing sand from an ancient fossil. So if a tree falls in a mathematical forest, and no universe exists to hear it, does it still fall according to an equation? Tegmark's idea takes this logic to its end, that all mathematical structures exist not in a metaphorical way, but in the same way our universe does. That the reason we find ourselves in a universe that obeys math is because only mathematical universes can host beings capable of noticing anything at all. In this view, there are countless mathematical universes, each with different structures, different laws, different geometries. We live in one where stable atoms form, where gravity is just strong enough to sculpt stars, where math and mind can meet. But if every mathematical universe exists, why does ours feel so special? Why these particular equations? Why this strange balance between chaos and order, between rigidity and randomness? Some believe it's a matter of selection. Most mathematical structures would never allow complexity, let alone consciousness. But a rare few like ours do. And in those, inevitably, questions arise. Civilizations look up. Minds wonder why. There's also the deeper mystery of how the universe knows to follow math. When we drop a stone, it falls not just with consistency, but with precision. It traces a parabolic arc as though solving a problem in calculus. But who is solving it? There is no blackboard in nature, no calculator in the void. And yet, somehow, the stone obeys. Maybe it's because the stone is not obeying math at all. Maybe it is math. A cluster of relationships, a knot of equations, a solution in motion. In this way, matter and energy dissolve into something more abstract: structure, form, relation. Even time might be a mathematical dimension, a parameter in a grand solution, rather than a river we travel down. If so, then the future already exists in the equations. Every breath, every star, every collision already there, just waiting for us to calculate our way toward it. This view can be dizzying. It strips the world of some of its texture, its grit, its romance. But it also imbues it with a strange kind of grace. If the universe is math, then it is flawless, not in the sense of being perfect or kind, but in being exact. It is a proof unfolding, a song with no missed notes. And yet, we don't always see it that way. There are moments that feel chaotic, cruel, senseless. And in those moments, the elegance of equations can feel cold. But even chaos has its patterns: turbulence in water, the branching of lightning, the beating of a heart out of rhythm. They follow strange attractors, fractal curves, hidden geometries. Even sorrow has a structure. Even silence is shaped by the equations that permit sound. Perhaps then, the universe is not made of things at all, but of relationships, of ratios, of symmetries and broken symmetries. We exist not as separate objects, but as parts of a formula too vast to write, a theorem in the shape of a cosmos. And if this is true, then we are not merely in the universe, we are the universe doing math, thinking itself through us, asking questions not just of matter and time, but of the nature of truth itself. What could be more beautiful? What could be more inevitable? In the hush that followed the universe's first breath, when everything was light and fury and blooming expansion, a quiet process began to unfold. Patient, steady, inevitable. It's called entropy, often painted as the agent of decay, the slow unraveling of order. Entropy is more than a destroyer. It's a sculptor, a hidden hand guiding the cosmos from the simplicity into complexity, from raw energy into stars, galaxies, and the delicate architecture of life. At its heart, entropy is a measure of possibility. It counts the number of ways a system can be arranged without changing its overall appearance. A neat stack of cards has low entropy. There's only one way to get everything in perfect order. But a shuffled deck? That's high entropy. 1,000 different arrangements all look equally random. In this way, entropy doesn't just mean chaos. It means freedom. It means options. In the earliest universe, when all matter was compressed into a hot, glowing plasma, entropy was surprisingly low. Everything was uniform, smooth, predictable. But uniformity is a fragile thing. As the universe expanded and cooled, small irregularities, tiny fluctuations in density grew. Gravity took hold of these fluctuations, pulling matter into clumps. Over time, these clumps collapsed into stars, stars gathered into galaxies, and galaxies formed the grand tapestry we see today. None of this would have been possible without entropy increasing. The universe had to let go of its perfect balance in order to become interesting. In a strange twist, the loss of order became the beginning of structure. We tend to think of order as something beautiful and disorder as something to be avoided. A tidy room, a well-structured sentence, a precisely engineered machine, all signs of control, of intention. But in the cosmos, disorder is the canvas on which beauty is painted. Without entropy, stars wouldn't shine, life wouldn't metabolize, minds wouldn't think. Consider a star. It burns by converting hydrogen into helium, releasing energy in the process. That energy flows outward, heating surrounding space, lighting planets, and eventually dissipating into the vast coolness of the void. This flow of energy from hot to cold, from concentrated to diffuse, is driven by entropy. The star dies, yes, but in doing so, it seeds the cosmos with heavier elements, the building blocks of planets, oceans, and blood. Its death writes the next chapter. Even the act of observation, of thought itself, increases entropy. To record a memory, your brain rearranges molecules, uses energy, and produces heat. Every heartbeat, every breath, every flicker of consciousness comes at a cost. Entropy is the price of existence. And yet, this process gives rise to astonishing order. Galaxies spiral with symmetrical grace. Snowflakes crystallize into intricate lattices. Living cells self-assemble from loose chemicals. How can disorder give birth to such precision? The answer lies in the flow. Entropy doesn't eliminate structure, it redirects it. As energy moves from high to low concentration, it creates pockets where complexity can emerge. These are called dissipative structures. They're like whirlpools in a river. Temporary, local zones of order, sustained by the flow of chaos around them. A candle flame, a thunderstorm, a coral reef, a brain. In this way, the universe becomes not a dying system, but a dynamic one, alive with motion, change, and adaptation. Entropy does not flatten everything at once. It allows small eddies of pattern to persist, to evolve, to become. And so we find ourselves in a peculiar position. We are made of order molecules arranged with almost implausible precision, yet we exist only because the universe is falling toward disorder. We ride the wave of entropy, surfing its gradients, building islands of meaning in a rising sea of randomness. This is not a contradiction. It's a relationship, a dance between what is lost and what is found. Over billions of years, the cosmos has moved from fire to form, from a smooth blaze to a star-speckled sky. Entropy has increased, yes, but in doing so, it has made room for complexity, for curiosity, for love. Every structure that exists does so not in spite of entropy, but because of it. And yet, the story doesn't end here. Someday, the stars will burn out. The galaxies will drift apart. Energy will grow thin and cold. This is the long view, the heat death of the universe, when entropy reaches its maximum and nothing new can form. A stillness beyond silence, a night that never ends. But that time is not yet. For now, the universe is still young. Stars are still being born. Planets still spin. Minds still dream. There is still warmth, still gravity, still the great unfolding. And entropy, far from being a villain, remains the quiet engine beneath it all. So the next time you see something beautiful, a tree trembling in the wind, a drop of water catching the sun, a thought that moves you, remember that it is not an escape from entropy, but its expression. The universe is not slipping into disorder. It is becoming. In the vast accounting of the cosmos, there may be no grander mystery than the question of how something came from nothing. Not just stars and atoms, but space, time, and the laws that govern them. For centuries, this paradox has challenged poets and physicists alike. How can anything exist if there was once nothing at all? And yet, beneath this riddle, there may be a subtle arithmetic at play, a quiet balancing act that makes everything possible, not by defying the rules, but by honoring them in the most elegant way imaginable. It begins with a simple, startling idea. The total energy of the universe might be zero. Not zero in the sense of emptiness or absence, but zero as a perfect equilibrium, like a scale balanced so finely that its arms hang in stillness, even as immense weights press down on either side. This balance is thought to arise from the interplay of two opposing forces: positive energy, carried by matter, light, and motion, and negative energy, bound up in the fabric of gravity and space itself. Matter, for instance, has mass and energy. A single atom of hydrogen, the most common element in the universe, contains within it the potential to light a star. Multiply that across the swirling galaxies, the endless constellations, and the result is an ocean of radiant, undeniable something. But gravity works in the opposite direction. It pulls, contracts, binds. And the more mass there is, the deeper gravity digs its wells. In physics, this gravitational energy is negative, not in mood, but in sign. It subtracts rather than adds. It leans inward rather than outward. So imagine then the early universe, a singularity, if it can be called that, balanced on the edge of being. As it expands, matter and energy burst forth in brilliant, accelerating waves, an explosion of positivity. But woven through this outpouring is gravity, pulling back, anchoring each atom with an invisible tether. The energy of expansion is matched by the energy of cohesion. For every spark, a shadow. For every push, a pull. This may sound abstract, but the math is surprisingly tidy. Some physicists, including Stephen Hawking, have speculated that the universe could be a closed system with zero net energy. All the mass and kinetic energy we observe is offset by the negative gravitational energy of the system itself. It's as if the universe wrote itself a check with equal parts credit and debit, and in doing so, didn't need to borrow anything from the outside. This opens a startling possibility that the universe could emerge from nothing, not by violating conservation laws, but by embodying them perfectly. From the outside, it looks like a miracle. From the inside, it's just balance. Negative energy, though counterintuitive, plays a role even in the vacuum of space. In quantum physics, empty space isn't truly empty. It seethes with virtual particles, flickering in and out of existence. Some of these fluctuations involve pairs of particles with opposing energies, momentarily borrowing from nothing, so long as they cancel out in the end. It's as if the universe is constantly whispering, as long as the sum remains zero, you're free to dance. This principle even allows for the existence of so-called negative energy densities, strange states predicted by quantum field theory. While we don't yet know how to harness such energy, it hints at deeper symmetries, places where the rules bend, but do not break. The concept of balance also resonates through Einstein's equations, where mass tells space how to curve, and space tells mass how to move. The curvature of space around a star is negative in energy terms. It traps objects, draws them in, and yet, this curvature is the very thing that makes planets orbit, light, bend, and time itself unfold as it does. The pull that seems to resist creation is also what enables its most intricate structures. Some cosmologists have even proposed that universes could bud off from quantum fluctuations in a kind of cosmic foam, many universes blooming from nothing, as long as they preserve that critical symmetry of zero net energy. In this view, our universe might not be unique, but one blossom among many, each balancing its own books in the silence between stars. This idea doesn't erase the mystery. It doesn't answer every question, but it changes the shape of the question itself. If the total energy is zero, then existence isn't a violation, it's a fluctuation, a balanced equation that happens to look, from our perspective, like galaxies and breath and the hush of wind through trees. And perhaps this is the secret hidden in the numbers, in the curving of space-time and the hum of particles beneath the surface of things. That nothing is not the absence of potential, but the perfect condition for everything to begin. That the universe didn't claw its way out of a void, but unfolded from it, like a ripple in still water, balanced, poised, inevitable. If that's true, then the universe is not a something rising out of nothing, but a dance between them, a perfect, ongoing symmetry, a whisper that said, "You may exist so long as, in the end, you leave no trace." And yet, here we are, suspended between the positive and the negative, between expansion and gravity, between being and not being, balanced, like everything else. At the supposed beginning of everything, there is a point the equations cannot cross. A boundary in the math, not made of matter or space, but of incompleteness. We call it a singularity, a word that feels sharp, precise, yet what it names is anything but. A singularity is where our models falter, where infinity creeps in, and where certainty dissolves into abstraction. It sits like a black dot at the origin of the cosmos, dense beyond comprehension, hot beyond measure, infinitely curved, infinitely small, and perhaps infinitely unknowable. The story goes that 13.8 billion years ago, all of space, time, energy, and matter was compressed into this singularity, a one-point everything, where the universe began in a flash. From this seed, the Big Bang was born, not exploding outward into space, but creating space as it expanded. Every galaxy, every atom, every moment flowed out from that inconceivably tight beginning. But as we peer backward with our instruments, tracing radiation, structure, and redshift, we can only get so close. Just before that first moment, the equations cease to behave. General relativity, which governs gravity and the shape of space-time, meets quantum mechanics, which rules the subatomic world, and the result is not harmony, but chaos. The numbers become undefined. Predictions lose their meaning. The curve of space steepens until it tears through the language we use to describe it. It is tempting to imagine the singularity as a real place, a physical speck waiting in the void. But it's not a place. It's a placeholder, a signal that our understanding reaches a limit, that something deeper, stranger, more unified must exist beneath our models, but has yet to reveal itself. Some believe the singularity never existed at all. Instead, they suggest the beginning may not have been a beginning, but a transition, a bounce from a previous universe, collapsing inward before rebounding into the one we know. Or a phase change, like water boiling into steam, as space-time itself shifted from one state to another. Others point to quantum gravity theories, like loop quantum cosmology, which propose that space and time are not infinitely divisible, but granular, woven from tiny loops or strings that prevent the collapse into a true singularity. In these models, the Big Bang becomes not a point of creation, but a doorway, and what lies before it may be as real as what came after. There are also theories that suggest the singularity is not in the past at all, but a kind of horizon, something we approach but never quite reach. In black holes, for example, a singularity is predicted to exist at the center, cloaked by the event horizon. But we cannot see inside. No signal escapes, and as matter falls toward it, the laws of physics twist into unfamiliar shapes. Perhaps the universe itself is like that. The singularity is not a single moment in time, but a horizon of understanding, one we forever near but never cross, a veil that keeps the ultimate origin just out of reach. In this way, the singularity becomes not a thing, but a boundary, a margin written into the story of reality that tells us where the map ends and the mystery begins. Even in mathematics, singularities are often treated with caution. In calculus, they represent points where a function spikes to infinity or drops into a void. In geometry, they mark sharp edges, discontinuities, places where smoothness breaks. And yet, these points often illuminate something essential. They highlight where assumptions fail, where approximations no longer hold, and where new thinking is required. The same may be true of the cosmic singularity. Rather than a flaw in the universe, it may be a reflection of a flaw in our tools, a sign that the patchwork of theories we've used to describe gravity and quantum mechanics is not yet a complete picture, that something more fundamental, more whole, must exist beneath them. In this sense, the singularity is not an end, but an invitation, an opening to a deeper understanding, still forming in the minds of those who chase the equations through silence and symmetry. It is a whisper from the edge of time, asking not just how the universe began, but why it took this shape, with these laws, at this moment. It asks whether beginnings are even real, or if time is a circle, or a spiral, or something we can barely name. It asks whether creation is a one-time event, or a continuous unfolding, whether the universe emerged from nothing, or from something so different it might as well be nothing. We may never know for sure. But we can follow the trail the radiation left behind, the patterns etched into galaxies, the ripples in the background glow of the cosmos, and get closer. Each measurement brings us nearer to the boundary. Each theory draws a finer map, and though we may never reach the singularity itself, we can learn from the way our understanding bends around it. Sometimes, the shape of a question is more important than the answer, and the singularity, real or not, gives us the most important question of all. How does everything begin? Perhaps the answer will come not in a flash of light, but in the soft convergence of ideas, a unifying theory whispered from the fabric of space itself, where quantum fields and curving geometry no longer clash, but sing together. Until then, the singularity remains a kind of cosmic poem, a dense line at the start of the universe, too compressed to unfold, too vital to erase. It is the silence before the song, the breath before the word, the limit of knowledge, and the promise that something lies beyond. The laws of nature shape everything we know. They guide the motion of planets, the flicker of atoms, the curl of smoke rising from a candle. They are so consistent, so reliable, that we've built entire civilizations upon them. Machines that fly, medicines that heal, clocks that count the breath of time. And yet, there is a deeper question that lingers just beneath the surface, almost too quiet to ask aloud. Where did these laws come from? Were they written into the fabric of the cosmos from the very beginning, coded into the pulse of the Big Bang like instructions in a symphony? Or did they exist before time itself, waiting silently for a universe to govern? In physics, we often take the laws as a given. We write them in the language of mathematics, elegant equations that describe how things behave, from falling apples to exploding stars. Newton gave us the rulebook of motion. Maxwell captured the dance of electricity and magnetism. Einstein bent space and time into curves that shape the orbits of galaxies. And quantum mechanics, strange and shimmering, tells us how particles flicker between possibilities, guided not by certainty, but by probability. But none of these theories tell us why these particular laws, and not others, hold sway. Why gravity follows an inverse square pattern, or why light travels at the speed it does. Why the constants, those mysterious numbers that appear in every equation, are precisely what they are. They seem arbitrary, yet the universe depends on them being exactly so. If any one of them were slightly different, stars might not form, atoms might not hold together, and life, as we know it, would be impossible. This precise tuning has led some to wonder if the laws themselves were selected, perhaps randomly, perhaps inevitably, or perhaps by something beyond our grasp. One idea suggests that the laws emerged with the universe itself, like patterns crystallizing as water freezes into ice. Just as the structure of a snowflake forms in response to temperature and pressure, perhaps the rules of physics emerged from the conditions of the newborn universe. In this view, the laws are not eternal, but emergent products of the universe's own birth, shaped by its geometry, energy, and unfolding dimensions. But others imagine the laws as more fundamental as timeless truths, independent of any specific universe. In this Platonic vision, the laws of physics exist in a realm of pure abstraction, waiting to be expressed wherever conditions allow. If multiple universes exist, as some theories suggest, each one might sample a different set of laws, like variations on a theme. Our universe, then, might simply be one where the music happens to sound like this. There is also a more provocative idea, that the laws are not fixed at all. Some physicists have speculated that the constants of nature might evolve over time or shift across regions of the cosmos. Perhaps what we see as law is only local custom, and in some far-flung corner of reality, the rules are different. Gravity might be weaker. Time might flow in loops. Light might obey a different script entirely. In this vision, the laws are not laws in the strictest sense, but habits, the consistent behaviors of a universe that learn to behave this way. And then, deeper still, is the notion that there may be no laws at all, only patterns that emerge from chaos, stability, born from randomness. In quantum cosmology, the vacuum of space isn't truly empty. It's a ferment of probabilities and virtual particles, a place where fluctuation is the norm. From this foam, order can rise, briefly and beautifully, like frost forming on a window pane. The laws we observe might be the survivors' patterns stable enough to persist, like ripples on the surface of a pond, even as the depths churn restlessly below. If so, the universe might be a kind of self-selecting system. Only those pockets of reality where stable laws emerge can grow, evolve, and be witnessed. And in those rare places, consciousness arises to ask why. There is also the idea that the laws are not external to us at all, that they are reflections of how we interact with the universe, shaped by the tools we use to measure, the questions we choose to ask. In this interpretation, the laws are not imposed upon reality, but drawn out of it, co-authored by the cosmos and the observer. They are not commandments written in stone, but relationships revealed one layer at a time. And yet, for all this speculation, the laws work. They hold. With astonishing precision, they predict eclipses and earthquakes, the spectrum of distant stars, the decay of atoms. They allow us to reach backward in time, reconstructing the moments just after the Big Bang, and to look forward toward the cold, slow dusk of distant futures. But the question of their origin remains. Were they born in the same moment as space and time? Were they carved into the void before existence began? Or are they illusions, emergent behaviors rising from something deeper still? Perhaps we are too close to see clearly. Like fish trying to understand the ocean, we may be swimming inside the very thing we're trying to describe. Still, the question lingers, luminous and unanswerable. Where did the laws come from? And why do they let us ask? There is a limit to how far we can see, a boundary not of matter, but of light and time. It's called the cosmic horizon, and it marks the edge of our observable universe, not because there is nothing beyond it, but because nothing beyond it has had time to reach us. The universe has only been around for 13.8 billion years, and light fast as it is, can only travel so far in that span. What lies past that horizon remains hidden, silent, veiled by the sheer slowness of causality itself. From Earth, we look outward in every direction, and we see galaxies, nebulae, radiation. Some of that light left its source billions of years ago, long before the Earth even existed. We are looking not just across distance, but into deep time. The farther we look, the younger the universe appears. Galaxies shrink into primitive forms, structures thin out, temperatures rise, until finally, all we see is a dim, uniform glow, the cosmic microwave background, the faint afterglow of the Big Bang itself. But even that glow has its limits. Beyond it, there is darkness, not because space ends, but because we have no access to what's further out. It's like standing in the center of a vast forest at night with a single lantern. The trees continue, stretching out in all directions, but past a certain point, the light can't carry. The forest still exists, but it might as well not, because we can never touch it. That distance, about 46 billion light years in every direction, forms a sphere around us, not because we are special, but because every observer, no matter where they are in the universe, carries their own horizon with them. The universe doesn't center on Earth, it centers on every point. And so the question arises, What lies beyond that horizon? Most cosmologists believe the answer is simple, yet profound, more universe. Galaxies we'll never see, light that will never reach us, perhaps even structures and variations far beyond anything familiar. The inflationary model of cosmology suggests that the universe expanded exponentially fast in its first instant, stretching tiny quantum fluctuations into cosmic scale structures. If that's true, then the observable universe is just a tiny patch on a much larger quilt, a bubble in a sea of bubbles, vast beyond imagination. But even this larger expanse is bound by our limitations. We can only theorize. We can't observe. The data stops, the map fades, and in that silence, possibility begins. Some physicists suggest that beyond our horizon, the laws of physics might change. The constants we consider absolute: the charge of the electron, the strength of gravity, the speed of light, might take different values elsewhere. If the multiverse an idea holds, then our bubble of reality is just one permutation among countless others. Some may collapse instantly, others may inflate forever. A few, like ours, may harbor stars, life, and consciousness. But if we can never access these regions, who can never send a signal or receive one in return, does it matter that they exist? This is a question of philosophy as much as physics. For centuries, the boundary between what is knowable and what is merely imaginable has haunted thinkers. Is the unseen real? Is reality confined to what we can measure? Or does it stretch into the abstract, the unreachable, the eternally beyond? The edge of observability is not just a physical limit, it is an existential one. It reminds us that our picture of the universe will always be incomplete, that no matter how advanced our instruments become, some truths will stay just out of reach. A kind of cosmic humility is required here. We are not omniscient beings gazing down from outside the system. We are part of the system, emergent, temporary, curious. And yet, we explore. We build telescopes that gather light from the edge of time. We measure the redshift of galaxies to infer the speed of expansion. We map the subtle anisotropies in the cosmic microwave background to reconstruct the early structure of everything. With mathematics, we extend our reach, creating models that hint at what might lie beyond. We simulate what we cannot see. We imagine what we cannot touch. Sometimes, in the silence past the stars, we glimpse echoes, gravitational waves from distant collisions, neutrinos ghosting through the earth, ancient photons warmed only slightly by their long journey. These are whispers from the horizon's edge, remnants of things that still reach us. But beyond that, a veil remains. There is something deeply human about standing at that edge, to know that there is more, and to accept that we may never know it. It is both humbling and thrilling, a reminder that mystery still exists. That wonder is not exhausted, and perhaps that is enough. Perhaps the value of the horizon is not in what it hides, but in what it reveals about us: our hunger to understand, our willingness to reach, even when the stars fall silent. In a universe where most of reality may be forever out of view, our small window matters more, not less. It is the portal through which we ask our questions, frame our theories, dream our impossible dreams. So we stand at the edge, looking out, knowing we will never see the full picture. And we keep asking anyway. The future of the universe is not written in stone, but traced faintly in equations, in the drift of galaxies, in the steady pulse of background radiation. Cosmologists do not yet know whether everything will one day collapse inward, stretch outward forever, or shatter apart at the seams. And yet, for all the mystery surrounding the end, there is a haunting possibility that the future might look strangely like the past. To see forward, we first look back. In the beginning, the universe was dense, hot, and unimaginably small. Not a point in space, but space itself compressed, brimming with energy, and expanding faster than light could chase its own tail. Time began not in silence, but in a roar of unfolding structure. As the cosmos cooled, matter emerged, then stars, then galaxies, then us. But what lies at the other end of the arc? If time is an arrow, does it ever return to the bowstring? One possibility is the Big Crunch, a universe that expands only so far before gravity reclaims its dominion. The momentum of expansion slows, galaxies cease drifting apart and begin to draw closer, stars collide, matter thickens, temperatures rise. Eventually, everything that once blossomed outward collapses inward, returning to a point not unlike the one from which it sprang. In this vision, time is a loop, not a line. The end mirrors the beginning, and perhaps, from that final collapse, a new universe is born. Some theories go further, imagining that this cycle could repeat endlessly. Bang, expand, crunch, repeat a cosmic heartbeat spanning trillions of years. If true, the present moment would be just one breath in an infinite rhythm, a ripple on the surface of a vast temporal ocean. And yet, this idea brings with it a puzzle. Would each cycle be identical, or would they differ? Would memory echo across universes, or would each creation be blind to the last? There is another possibility, one that stretches not in loops, but in lines that never return. The universe may be expanding faster than we ever expected. Dark energy, a mysterious force that repels gravity, seems to be accelerating the cosmic stretch. If this continues unchecked, we face a future called the Big Freeze. Over trillions of years, galaxies will drift beyond each other's light. Stars will burn out, one by one, leaving only cooling embers. Black holes will evaporate into nothing, and the universe will slide into silence, cold, vast, and empty. Yet even here, in the silence, there is an echo of the beginning. The early universe was a place of intense uniformity, smooth, hot, and simple. And the far future may be similar, a uniform sea, this time not of fire, but of frost. No stars, no complexity, just evenly spaced particles drifting through expanding space, echoing the balance of the first moments in reverse. A symmetry not of shape, but of stillness. Then there is the Big Rip, a stranger end still. If dark energy's strength increases over time, it could eventually overcome all forces, even those that hold atoms together. Galaxies would tear apart, stars would unravel, planets would dissolve, and finally, even space and time themselves would rip into pieces. This would be no gentle cooling, no graceful collapse, but a violent unmaking of all structure. And yet, in its chaos, there is a reflection of the early universe's unpredictability, the raw primal energy that seeded all form. Whichever future awaits us, each path seems to circle back to the same philosophical mirror. At the edge of time, something always feels familiar. Whether in fire or ice, in crunch or rip, we are haunted by the symmetry between first and last. And perhaps this is more than coincidence. Some physicists propose that time itself is a kind of emergent property, a feature of entropy, the spread of disorder. If that's true, and if entropy truly reaches a maximum at both ends of cosmic history, then the distinction between beginning and end might dissolve entirely. The universe could look the same, whether viewed forward or backward in time. The arrow might be a loop, or a reflection, a palindrome of existence. But these are not just scientific questions. They are deeply human ones. We wonder about the end because we know we have one. We study beginnings because we came from one. The story of the cosmos is, in some strange way, our own. Our bodies are made of atoms forged in stars. Our breath carries echoes of ancient hydrogen. We are the unfolding of the universe, asking about its destiny because we are its memory, its witness, and its voice. And so we look to the skies, to the data, to the math, hoping to catch a glimpse of our future in the patterns of the past, not to escape what is coming, but to understand our place in the great rhythm. To feel, even for a moment, the sweep of time as a whole, not just as moments ticking by, but as a grand structure, elegant, mysterious, and perhaps, in its shape, circular. The end is coming, but it may not be an ending at all. There was a time when nothing existed, no stars, no galaxies, no time, no space, not even the rules that make such things possible. And yet, here you are, sitting, breathing, listening to a voice move through vibrations in the air or flickering pixels on a screen, carried across space by machines crafted by minds like yours. This moment, this awareness, this delicate self, it should not be here. And yet it is, you are. That is the deepest mystery of all. We spend so much time peering outward, tracing galaxies and particles, watching cosmic dust swirl into stars, and listening for the whispers of the Big Bang across the sky. But sometimes, to understand the universe, we have to look inward, not just into telescopes, but into mirrors. Because the truth is, you are not separate from the story we've been telling. You are the story. You are made of it. Every atom in your body, every carbon, calcium, and iron molecule was forged in the heart of a star. Not metaphorically, literally. Stars lived and burned and collapsed so that your bones and breath could exist. Hydrogen fused into helium, helium into heavier elements, and when those stars exploded, they scattered themselves into the dust that would one day become planets, oceans, blood, and breath. The iron in your blood once glowed white-hot in the core of a collapsing sun. The calcium in your teeth once drifted through interstellar space as powder and ash. But go deeper still. Those atoms weren't always atoms. Before they were matter, they were energy fluctuating patterns in a sea of probability. Virtual particles flickering in and out of existence from the quantum foam. Ripples in empty space that, under just the right conditions, became something more, became matter, became memory, became you. You, the listener, the dreamer, the pattern of thoughts within a fragile brain of stardust, a conscious echo of something so ancient we barely have words for it. The strange and beautiful truth is this: the universe was not just capable of producing you, it may have required you. Not you specifically, but awareness, reflection, an entity capable of turning back to look at the cosmos and say, I see it. A being that could ask, why? And that asking, that ability to wonder, is not a trivial thing. It is the only way the universe can contemplate itself. Without life, without sentience, there would be no questions, and perhaps no answers either. You are not outside the universe, examining it from a distance. You are inside it. You are made of it. You are a function of its laws and its accidents, its beauty and its terror. You are the breath and the echo. You are the evidence that it happened, that it still is. In a universe that may last trillions of years, your time here is brief, a single flicker. But in that flicker, you do something extraordinary. You notice, you record, you remember. And perhaps that is enough. Perhaps that is everything. We have spoken about beginnings, about singularities and foam, about fields and entropy, about the mysterious rules that govern nothingness and everything alike. We've wandered through ancient myths and the frontiers of physics, tracing threads back to the earliest dawn and forward into the endless night. But here, at the end of the story, the question comes full circle. Why is there something rather than nothing? Some believe it's a cosmic accident. Others, a necessity of mathematics. Some say it's the mind of God. Others, an infinite chain of births and deaths with no beginning at all. But all of these theories, elegant, strange, comforting, or cold, share one thing in common. They produced you. And you, in this quiet moment, in this moment of reflection and stillness, are proof that the universe is not just structure and spin, not just void and vibration. It is also awareness, wonder, witness. Your heart beats because a star died, Your thoughts dance because quantum particles once jittered into being from nothing. And now, billions of years later, you are here listening, dreaming, wondering. And that may be the most miraculous fact of all.